My name's Kevin, and today I'm going to be talking about developing an eye-tracking-based dyslexia indicator. Now, I'm a senior software AI engineer at Red Hat, and yeah, let's get into it. So, dyslexia. The problem with dyslexia today, up to 10% of the world's population is diagnosed with dyslexia. But something a little bit more worrying than that is another 10% on top of that is undiagnosed. Now, reasons for that can be because the high costs to go to a psychologist, get diagnosed, it's very expensive. As well as that, there's other issues such as social factors. People are embarrassed about saying that they have a hidden disability. And as well as that, there's also a lack of resources, potentially for teachers, to actually do this early identification of dyslexia. So what does this mean? This means that there's a need for innovation. We need something that's more accessible, that's cost-effective, and that can actually diagnose them early. So the history of dyslexia, back in the 90s, in the 90s, there's really no dyslexia. Wasn't really a thing back then. They'd kind of be like, okay, this person can't really read well. But then from that in the 1960s, they really started to establish more formalized patterns such as reading skills and phonological testing, so such as speaking. And this is standardized testing, but this is quite objective to the psychologists and was quite costly. From there, we then go into the 90s to early 2000s, where the emergence of neural imaging came, where they could actually identify the differences between a typical and atypical brain firing, different uses, parts of the brains that are being used. And this really gave way to identifying the differences between dyslexic brain and how it functions. But this is quite complex and expensive. So from there, in the 2000s to 2010s, this is really where the magic started to happen. This is where machine learning and eye tracking came together. Now we're able to find a cost-effective way to actually find these trends within dyslexic people. And this leads way to our research today. So today, we're going to be taking a data set, a generic data set that is effectively, it could be anyone. They're not dyslexic, and we're going to classify it as either individuals being dyslexic or not based off a certain parameter. From there, we're going to go into clustering. We really want to validate this data that we cluster and find potential insights from this. Finally, once we find the insights, what we want to do is create a model that will effectively be able to say, you may be dyslexic to a certain percentage. So from there, we start off with our data set. Now, it's really important that we do this properly. So we used the Provo corpus. So this is from the Birmingham Young University, and this is just tracking eye movements during reading. Now, this is people from the university, and they have 20/20 eye vision, as well as that they're native English speakers. This data set's broken down into two parts. First part is the predictive norms. This is 470 participants, and they were given text like, so they're given 55 texts, but the texts would contain blanks in them. So, for example, let's say I say, I want to go to the, and then people have to put down what they think would be next. They aggregate all this data, and then this gives the prediction of what is most likely. This data set's then merged into the main data set that we're going to be using today, which is the eye tracking data. And that contains 84 native speakers. They're aged between 18 to 25 years old. Half of them are male, half of them female. And they were just tasked with just simply reading the text while a camera was pointing at their eyes. Now, this gave us metrics such as fixation, such as what words they're looking at, saccades, such as the movement of their eye, and regression, how many times their eyes jump back and forth. So this is a large data set, 63 columns and 230,000 rows, which means that there's a lot of insights to get from this. So this means that there's a lot of cleaning that has to happen. And I'm not going to run through this in detail. I'm going to do it briefly so we can go to the more juicy stuff. So first of all, we start off with a little bit of missing value imputation. We use a little bit of machine learning. Depending on use cases, we majority of the time used more simple mean mode and median imputation. So from there, we then go into duplicate values. Since there's so many rows, these duplicate values can really cause high variance, which is not good for when you go to the training phase. Likewise, with multicollinearity, it kind of links in. If two values have similar attributes, then this will cause high variance, which is not good. So from there, we also go into feature transformation. Basically, what happens if we have a value such as start time, end time. Well, we have loads of values, and we really want to reduce this down because lots of values in rows means high computation. So what we can do is if we have start and end time, we can just get rid of those and create one that says duration, which combines both of them. As well as that, we also created other features such as like TFDI or anything else that may enhance our data set. From there, we've had to validate our changes and then to ensure the integrity was all good. So now we have our data. Now you can actually get into the fun stuff. Let's actually start trying to classify this data into dyslexic and non-dyslexic. So initially, our approach was, how do we do this? So we had to go through existing research papers and figure out what are the traits within our data set, what are the features that are going to indicate this. And we've come up with a list on the left-hand side of this grid here. You can see that we have circadian amplitude, basically the initial movements of the eyes, dwell time, how long you look at the word, IA fixation, so basically when you look at the text, progression in and out, how many times do you jump forward when you look at a particular word or jump back, and then circadian duration, how long does it take for your eyes to move from word to word. So we found basically this on the internet, and great, now we have the features that we need, but what can we do with this information? So we had to look into even more, what do we do with a generic data set? So for each of these, basically there was traits with them. Basically, if you have greater than than the average, then it's more likely that you could have potentially dyslexia or be a very poor reader. So from here, we effectively followed the trend that the research was doing, which was take the 95th percentile, so some of the poorest readers, statistically for each of these metrics, and combine them together to create a threshold. This threshold then determined basically 1 or 0, a brand new column, basically they're dyslexic, not dyslexic, or potentially if that doesn't work, then we could say they're a poor reader, for sure. So from there, we had to basically pick out the best 3 out of the 5, because what we need to do is once we use these to create this brand new dyslexic, non-dyslexic column, we have to throw away that data, which isn't great because we still need some of this core information when we're training a machine learning model. So from there, we did some experiments and we found that the top 3 that are key at identifying dyslexic, or a poor reader were the first 3 that you can see highlighted. So we ran the experiments with that, and in the end, we got 10% of our data being poor readers, and then we got 90% having no difficulties reading, which aligns with the initial figure that I said to you in around 10 to 20% of people are dyslexic. So that was a promising find, but we actually want to dive a little bit deeper. We want to actually validate this information and see if there's any trends that we can find within this clustered data. So we ran 3 experiments. You can see in the circles. So we ran it with all the features. Basically, can we see from a very high-level view, can we pick up any trends? But then we want to drill down a little bit deeper. From the selected features that I showed you earlier, you can see, is there any trends amongst that group? And then we keep going in more and more detail. We go down into the dyslexic features. Can we see potentially it's not just you're dyslexic or you're not dyslexic? Potentially, is there a spectrum? Is there basically like different severity levels? Can we pick that up graphically and represent that? Because if so, then we could potentially do tailored intervention, which I believe hasn't been done before. Then finally, we want to do a little like control group for the non-dyslexic. We want to see, is that different from the dyslexic group that we have? So anyway, we start running through this experiment. They all go through the same process. They go through data processing, feature normalization. For a cluster algorithm we use is hierarchical clustering. We use that with Euclidean distance and word linkage. And we use what do we use? We use the elbow method to determine the optimal number of clusters. After that, we do method called cluster profiling, where you effectively look at each of these clusters that are generated and figure out the traits so that we can actually determine if it's useful or not. Then we just do some dimensionality reduction so we can actually visualize it. So here are the results that we have. So as you can see in the top right-hand corner, that from a high-level view, there's not a lot going on. It's quite dense. But after doing a little bit of cluster profiling, we can see that the purple section represents the better readers, yellow a little bit more moderate, and then the green a little bit more struggling, but it's not conclusive. When you actually look into the selected features on the right-hand side, we can actually see a lot clearer picture. We can see that after cluster profiling, we can see that the green represents the normal, not people who aren't affected, but don't have reading difficulties. Then we see a slight variation with the purple this time around. These are people who are a little bit more mild, they struggle, but may not affect too much. And then you can see at the very top with the yellow, you can see a lot more sparse, different reading abilities. And there the people who are potentially dyslexic or have very poor reading abilities. Likewise, when you start delving a little bit deeper, you can actually see that there's different clusters forming, which showing that there is actually a spectrum at different levels of severity. And the promising thing that we see for the non-dyslexic readers is that there's one big block, which shows that there's not too much variance amongst the people who we classified as not poor readers. So from that, we can go in. Now that we found that there's actually some sort of trend that's there, what's really good at picking up trends? Machine learning. So we're actually going to start doing some feature ranking. So we're going to use a random forest model, which is quite simple, lightweight model, classifier, and we're going to start doing some feature ranking with it, basically determine which are the most important features. So at the moment we're working with 63, and we want to reduce that down. So we create a threshold of 75%. If the F1 score does not hit that, then we will take it away. And then we move on to hyperparameter tuning, basically find the best parameters for the random forest model. After that, we go into forward selection. The reason for forward selection is that we want to reduce this down and also improve the accuracy, because at the moment, I believe that having 44 features, there's bound to be some features in there that are actually taking down the accuracy. So forward selection is basically you take the first in the list, train it, and then iteratively build upon it. If the next one combined with the first one reduces the accuracy, then it is discarded. So this continues until it goes through the entire list, and we have the best accuracy. So we're able to go from 44 down to 12, which means that people in the future, everyone recreate this experiment, they can do it a lot quicker and efficiently. So from there, we then go into model evaluation and training. So we start training the model, that's great, get a high accuracy, good. But then we have to evaluate it. So we did 9 k-fold cross-validation, where effectively chunked up their data into 9 different experiments. And then I can show you the results. We visualized it. And so we got an F1 score of 88.43, which is quite high compared to the other ones. It's not the state of the art, but we use a quite lightweight model. The state of the art at the moment is this convolutional neural network, which is quite heavy. They did clinical trials and got around 96%. We believe that if we actually use dedicated dyslexia data after doing clinical trials, using the same methodology, we could potentially get higher or close to using this lightweight model. But you can see from our basically receiver operation characteristic curve, you can see the k-fold experiment. So you can see that our line, so there's an average line of 96%. You can see all our other experiments are actually overlapping with each other and are very close, which shows very high reliability, which is what you want to see. As well as that, you can see the accuracy score, precision, all that is aligning in the same results, which shows a consistency. So today, I presented basically a dyslexic tool, or poor reader tool that potentially people could use and build upon. We also showed a classification framework, potentially to take non-dyslexic data and taking a generic data set and actually converting that to a dyslexic data set. As well as that, I also showed you some cluster analysis, some trends showing that there's different reading abilities potentially within the dyslexic field, and potentially we can do tailored intervention for that based on this research. So with that, I want to thank you, and yeah, great. We have 2 minutes, so finished early. If there's any questions, feel free to ask. Hello?
Hi. Who is paying for all your exploration investigations? So is there a group of people who is financing this, or
Yeah. So
Red Hat the one who's paying? Or?
yeah, good question. So yeah, basic question: who's paying for this research I'm doing? So this was actually part of my master's. So this was actually personal research that I did. And basically just kind of brought this knowledge and insight.
So there was no payment for you?
There's no payment for me, but this was more of a passion project, I suppose, for myself. Yeah, I share a startup that's related to this, so that's where the idea came from. You never know. If someone's interested, give me a call. So. Hello. That's a really good question. From research, so basically, can these questions be related to other languages such as German and other languages? Really, it's with English and stuff. Latin languages generally tend to keep consistency. From some research actually showed that there's a slight difference with German in particular. But yeah, I haven't done research with that, but there should be some consistencies amongst that, some trends that actually could overlap. I mean, at the end of the day, we're just picking up eye tracking movements. So that's kind of the form that we're using. It's not really based off language, it's based off how your eyes move. But yeah, we're out of time anyway, and yeah, thanks.